Okay, guys, take it away.
Okay, yeah. I'm planning something like this on efficient net. Probably I'll start with the paper and explain maybe each section, which is, I'm planning to explain from abstract to results section, and maybe then and then we can, then and then we can have a discussion on if anybody has any question on the fly. And then so when I explain when I explain architecture details in the paper, I thought of going a bit of architecture implementation. How that looks like, so that gives kind of a good understanding on the architecture that we have. Efficient architecture that we have. And this, I'm going to explain. This paper talks about the base of efficient architecture. So on top of that, there are some improvements recently have come up. So, and everything captured in the maybe TensorFlow TPU implementation from Google. So I'll be showing the references around it, and maybe we can see the improvements and the, what caused to improve the accuracy further. So that's the agenda that I'm thinking. I hope that should be fine with everybody.
Yeah, sounds good.
Okay, yeah. Looking into the paper, this is the first version of the paper released maybe 2019, I think, 19 somewhere, or I think 19. This whole paper, their maybe intuition is only one thing, that is how to find out the compound scaling method. So the only approach that they built in this paper is how we can come up compound scaling method. So we will see what is the compound scaling method and what advantage it gives having the compound scaling method. So if you see the if you see the abstract they talk basically there are two things in abstract that they talk. It is like a balancing between the depth, width, and resolution when you build a network, when you design a network. That is how they came up a method called compound scaling method. And once you have compound scaling method in place, what benefits it give? So benefits in the sense we might be getting a benefits in terms of the number of parameters and how much accuracy it boosted up. So these are the two things that you can see in a figure 1. So it talks about a model size versus accuracy. Accuracy in the sense that they have taken ImageNet data set as the as the base data set, and on top of it they have run a different models. And this plot, this diagram shows how many number of parameters each model has and what is the accuracy that they have achieved. If you see here, the blue, it is a kind of amoeba net that they're talking about, and the dotted, if you see, that I think inception to SCNet, how progressively they have improved the accuracy by increasing the number of parameters. So whereas if you see the line which shows in red, there are different there are different variations of efficient net, which starts from B0 to B7. So B0 somewhere 70, 77 or 76, 77 accuracy, and then accuracy went up to close to 85 when you see the efficient net B7. But in terms of the number of parameters, it is somewhere 66 millions, I think, which is far far lesser than the SCNet or amoebanet that you can see here. So this is the achievement. This is the thing that they have achieved using this compound scaling method. Just having the base network from there. Just to improve the scaling method. Each version, it's just improvement in scaling method, the compound scaling method. So then, if you see the Introduction, basically, introduction, they mostly talk about, I think we have in the previous sessions, if I remember correctly, we spoke something about the RESTnet. Then if I remember correctly, we talked something about STnet also, the SPs and the excitation blocks also a bit. And I think somewhere they have mentioned the inception and these kind of architectures. If I remember correctly, earlier discussions, we have seen those kind of networks. So but the good thing in this paper is, given a literature in image recognition, basically image classification literature, they have a split based on the, I mean, accuracy, efficiency, and scaling in terms of the depth. I mean, if you increase the number of layers, we know that, I think everybody knows that the accuracy and the goes up. But we don't know what is the max limit. I mean, we cannot increase the number of layers infinitely and see, and we don't expect, I mean, we don't see the benefit. That's what mostly in the ResNet we have seen, and they have increased from as here, as shown here, ResNet 18 to ResNet 200. So this is kind of increasing the depth in terms of the depth. So whereas if you see gpipe, there is a paper called gpipe, in which they increased the resolution. So in maybe on somewhere LXNet or VGGNet, we have seen it started with 224 by 224 by 224 or 227 by 227. And, I mean, on which resolution network run through. But in gpipe, they have increased the resolution, but there are drawbacks behind that. So that we will see later. And this is with respect to resolution, ResNet with respect to depth. And similarly, if you see, there are some wide residual network which talks about increasing the wide in the sense number of units in each layer. So, I mean, if you see the entire image classification literature or image recognition literature, the people have been experimenting in terms of the depth, in terms of the width, in terms of the increasing the resolution, and see how the network affects. I mean, whether it increases the accuracy or decreases the accuracy, and what effect it gives. So that is one, and the people have been experimenting, I mean, since last couple of years. So in this paper, they have summarized everything. So they have summarized, and they try to see, is there any, I mean, they try to see, is there any principal method in which they can scale up the depth, width, and resolution. That is what whole paper talks about. So people earlier, they just concentrated on depth, some people concentrated on width, some people concentrated on the resolution. But here in this paper, they have studied what is the best way, a principled way, in which we can scale up all three. All three. It is because each one they have seen, it is increasing it is boosting up the accuracy, but when nobody concentrated on all, and I mean all, increasing all at a time. So this paper mostly analyzes the method in which, how feasible it is increasing all three together. So that is called compound scaling method. So that it just named as a compound scaling method to scale up the width, depth, and resolution for, while designing a network. So if you see this diagram, the first one here, it shows the baseline. Baseline in the sense, you just take a resolution, some resolution, and you design some with some number of layers by having the some width in each. This is the base. So you might get some accuracy with this network, with the baseline network. Then by taking this baseline network, you try to increase in terms of the width, number of units in each layer. Then this gives some boost up in accuracy, but it obviously causes maybe more memory. In terms of the memory, it is high. In terms of the computational complexity, it is high. So, and next they increased the depth in the sense number of layers in each, in this base layer, and it is also increased the in the accuracy. But it has got its own flaws again in it. Flaws in the sense, I mean, drawbacks in it. So again, they have increased the resolution and run through base network, and I mean, they have seen some benefit behind it. Now, as we have seen individually, in terms of the width, in terms of the depth, in terms of the resolution, if you modify, the network started giving the a better accuracy. So they have mixed up everything, and they have found something called compound scaling, in the sense they have taken some ratio. So they have taken some ratio, and they have designed some network using this compound scaling, which gave a better accuracy and better generalization, and generalization when they run that network into the testing data. So that is, this whole picture talks about this intuitive approach that they have built in this paper. So next, actually, this again they talk something about mobile nets, then REST nets, then uh, one more thing that I have not spoken so far is a neural network search, which is a kind of AutoML framework that Google built again. They have used this. They have used that as well in this paper. I mean, in this experimentation. So that is one thing that they speak in this section. And yeah, I mean they are just telling the in terms of the improved, I mean, top one accuracy, how much it benefited. Then in terms of the flops, and the flops, how much it benefited in this section. Then when you go to the related work, which is where I really I felt it is good that the way that they captured here. So convenient accuracy, I mean, in terms of the accuracy, what are the networks that they give accuracy benefit? I mean, if you see starting from AlexNet, so and running through an ImageNet, maybe next week through kind of GoogleNet, so which gave kind of a state of the art that time. Then people have done some changes in the SCNet, the way we have seen. I mean, the squeeze and excitation block they have added. So then that gave a good benefit in terms of the accuracy. Then Gpipe is the one which is I mean again beaten up the SCNet. So like this, they have kind of mentioned the each and every stage. I mean, every stage, what are the what are the good architectures that caused, I mean, that caused accuracy improvement. So in this entire section talks about talks and gives some references at what stage, at what network architecture gave good accuracy. So when they designed the I mean convenient. So that is a kind of summary that they have mentioned in the convenient accuracy section. Then if you go further down, so then next they have mentioned something at efficiency. First section, I mean, it is something they concentrated how to improve the accuracy by just increasing the number of layers, or increasing the width of the network, or increasing the resolution. The next section talks about, I mean, once you increase the number of layers on a number of units in each neuron, in each layer, and resolution. So the problems that we face might be in the increasing the model size. Maybe we need to have a, I mean, well, so kind of supercomputers from the very high level GPUs, all those things. But in the next section, is there any, I mean, they studied something kind of this literature. If you see, they studied something kind of how we can efficient, I mean, we can make efficiency in the sense, is there any possibility to reduce the model size? Maybe, for example, we can apply we can apply the quantization kind of something they call the model compression. Then people have come up a kind of depth-wise convolution, which is kind of mobile nets that they have come up. Then squeeze nets, shuffle nets. These are all kind of they concentrated something on how to improve the convolutional neural networks efficiency. So this section completely gives the papers or literature. So which approaches concentrated on the convolutional efficiency. Then the third section, third section, if you see, it is a kind of model scaling. So model scaling in the sense, I mean, again, it is a kind of related to kind of depth. So for example, ResNet, if you see, they have different variations in it. So from 18 to 200, as I mentioned earlier. And again, a wide ResNet, if you see, it is kind of wide. I mean, widely how to improve accuracy by increasing the units in each layer. So it is a kind of a scaling that they talk here. But the question remains same. The question is, is there any better way or any better approach in which we can improve the altogether? I mean, scaling, efficiency, and I mean, accuracy altogether. Is there any way that we can improve? That's what they have completely studied in this paper. So that they named it as EfficientNet. So this still here we have seen kind of earlier literature before they came up efficient nets that they spoke about a literature completely. So then the actual method that they came up here, they talk in section 3, which is called compound model scaling. Probably I just park here and see if anybody has anything to add, or maybe.
I have a question.
Yeah.
So efficiency, they define efficiency as just accuracy by parameters divided by parameters, accuracy per parameter ratio, or what's the definition of efficiency?
One way, if you see mobile nets, yes, as you said, they have looked into the number of parameters that you see. I mean, when you see the difference between fully convolutional network and depth-wise convolutional neural network advantages, we will get number of parameters less. So that is a one thing. But the other two things, if you see, once you get the model, how to disable some neurons which are not really required, that they maybe that they call as a model compression. So, and I'm not really gone through what squeeze net and shuffle nets and I mean, I think neural network, auto ML or neural network, NAS nets, of people say, neural architecture such, which is a kind of, again, it is completely how we create a such space. For example, we are, while creating such a space, we can define, we can give a high threshold to the accuracy, or we can define the. I mean, there is a provision to define the, to reduce the number of flops also. So that is what mobile net version 2 that they talk about. I mean, they have considered the processor on which the architecture runs through, and take that as a one parameter while searching for a network. So yeah.
I have a question that may jump ahead a little bit. Does the neural architecture search, this seems a lot like AutoML, traditional AutoML construction. Do you, and this is where I may jump ahead, does neural architecture search allow you to construct a neural network that would have some level of interpretability? Would it be easy that once the final model is built, that the coder can look at those parameters and those hyperparameter choices and say, okay, here's what I think the model has, how it's constructed itself following this neural architecture search approach. Therefore, I understand ABC about the data or about the predictive function. That was the question. Yeah.
I'm just thinking. I don't know. If I understand, you're saying it is a kind of post-processing that you're talking about. I assume it is a built architecture. I mean, it is a built architecture with some number of hyperparameters. Then you're saying on top of that, you're saying from that hyperparameters, you want to know something. That's what you're
that is my question. Yes. Yes.
Okay. I am not really sure actually. I know how to find out hyperparameters. I mean how to design a neural architecture such to find out the hyperparameters. But once you have hyperparameters, it is a kind of reverse engineering that you're talking about.
Yes.
No, I don't have maybe right answer to your.
Mash, are you talking about hyperparameters or parameters? Because model interpretability will be kind of related with parameters, right?
Parameters, yes. It would be more of the parameter choices, I guess, not the hyperparameters. Correct. I didn't word my question very well either.
No. Okay.
So I think interpretability really depends on what. So that's, in other words, like what we were sharing right now. It's like, is efficient nets interpretable or not?
Yeah.
And I think the answer in this case is yes.
Yeah.
Okay.
But when you say yes, Bechtel, it would mean yes in the in terms of explaining how you get the value of the parameter, right? Not the how
No,
the
not with the value of the parameter, right? Value of the parameter would be SGD. So that is not the interpretability part, right? It's kind of like, let's say, heat map. So I'm saying interpretable in that way, or you can see what the initial layers are doing.
Yeah.
Mm-hmm.
That sort of way I'm saying, yeah, probably it's interpretable.
So would efficient net only be useful for, because it's convolutional neural network, would it really be ideally suited for images or some kind of image-based processing?
Yes,
Yeah.
from my
But I think yes. Yeah. For that answer is yes. I think it is for only kind of image data. It can be used for image data only.
You could probably use the same ideas for something else, but yeah, if you're using efficient nets, it's purely convolutional based. So yeah, image stuff.
I think I mean, if you have come across recently scaled YOLO V4, people have come up.
Mm-hmm.
I think 2 weeks ago they have released a paper called scaled YOLO V4. I think they have come up same thing, same kind of search based. I think so. I mean, efficient depth also it's the same. I mean, it's same concept. I think in terms of the object detection, this is for image classification. I think those two are for object detection based on the same concept. But I'm not sure if there is anything present in terms of the text data or audio side.
Mm-hmm. Mm-hmm.
I'm not sure if maybe if anybody has something on this concept, maybe, but I'm not sure if something present on the audio or text data.
Got it. Thank you. Thank you very much.
So yeah, with that, the actual crux of the on the net, paper is here. Something, as I mentioned, it is compound scale model scaling. So in this section, first part is the entire convolutional neural network design. They formulated as a they formulated here something like this, and as equation 1. If you see the equation is a number of, it is a composition of number of layers. Those are present in a network. N is nothing but a number of layers, composition of number of layers. If you see here, this is a spatial dimension, height, width, and channels, and X is input, and the Fi is nothing but the operation that you apply. Either it can be convolution. It is everything as aggregated one. Convolution, activation, and the activation map, everything they represented something like this. And they formulated everything, the convolution CNN design as equation 1. That is what they says here. Why they have done this one is, they want to formulate this compound model scaling. So as mentioned in equation 2. So once you have n here, n is nothing but the number of layers or number of layers output that present here. So once that output is accuracy, right? It's accuracy that we are looking for given a convolutional neural network. So that accuracy we need to maximize given a depth, width, and resolution. That is what they talk in the equation 2. So here, if you see, the entire intention here in this paper is how to maximize accuracy given a base network. So here, in terms of the accuracy, and then in terms of the memory, if I'm not sure, I have run through, I have used a pre-trained model. I have used the transfer learning, and I have used my own, creating my own model with my data, but I have not seen how to do this. Given a target memory, making sure within the target memory. Here it is something like, given a target memory, we need to make sure that it should be within that memory, even the target flops also. So this I'm a bit skeptical. I'm not. I tried to search what is the way, but it might be hidden in the neural network. I mean, the NASNet paper, that MNES mobile network neural networks such that they have referred. It might be hidden in that, but as such, here it is a kind of threshold in terms of the accuracy, threshold in terms of the memory, threshold in terms of the flops. So altogether that they captured in the equation 2. So and again here the number of here the important things that we need to consider again is length, width, and resolution. I mean length in the sense the depth of the network, width, and resolution. Those are the things that they focus in this problem formulation also. So next, once you have this kind of problem formulation, so here if you want to improve the accuracy, the parameters that we need to pass is, so what is the depth? I mean, how many layers we want to design? And next, what is the width? How many units, neurons in each layer that we want to pass? Again, the resolution. The resolution, how much is the resolution that we want to use? So for that, they have done something again, scaling dimensions here. Again, it's the same kind of, and I really don't see the difference between the literature related work that they have mentioned and this depth. I mean, if you see there is a kind of overlap between the that section and this section. Depth, they have given same references kind of, but only thing that they have mentioned here, the deeper convolutional nets can capture richer and more complex features and generalize well on new tasks. So this is kind of, again, they might have brought from the old literature, old literature itself. So that is the one concept, and they have used some to generalize the network well. It is kind of skip connections that we have referred already in the ResNet, and the batch normalization. These things they have mentioned in the depth. I mean, in the depth case. So when you increase, it is because when you increase a depth, our assumption is we might fall into the vanishing gradient on the problem, something that might occur by default. So to reduce that, we can use these kind of techniques like batch normalization as skip connections that they have mentioned in this section. Next, going to the width, it is kind of, again, they have referred something wide resolution network. I mean, the same references. Then the only thing that they have mentioned here is wider networks tend to be able to capture more fine-grained features and are easier to train. So earlier, the deeper network, they says that it is, I mean, the deeper, it learns more complex features and generalize well. And the wider network, it is a kind of learns the fine-grained features and it is easy to train. Again, that this intuition they might have derived from the old literature only. So the third part, it's a kind of resolution. I mean, they have done some experimentation. As I mentioned earlier, we have started somewhere maybe 224 by 224. Now, if you see the efficient at L2, it is a kind of 800 by 800 resolution. We can pass it to the network. So they have seen when they increase the resolution, they have seen a benefit out of it. So that is a third intuition. And overall, if you see the observation that they made is scaling up any dimension of network with the depth or resolution improves accuracy, but the accuracy gain diminishes for bigger models. So there is a certain limit. I mean, we cannot increase infinitely. There is a certain limit. So after that, it saturates. I mean, it is not going to give any benefit. Maybe it might diminish also. That is what their first observation. Till when they have experimented around these three factors. So then going further, I mean, after this observation, then they started again what can be done by considering, I mean, what scaling factor we need to add. See, for example, if I use 224 by 224, what the depth is, what kind of depth I need to have a network, what is the width of my network, and the resolution anyway it is fixed to 224 by 224. So these things comes into the picture in the compound scaling. That's where they have kind of come up something like this. So this here, this is completely with respect to system resources that are available. For example, if you want to design a network which is at certain depth and certain width and with certain resolution, the system also should be capable enough to train the network or run the inference. So if we don't have sufficient resources, for example, memory, or if we don't have a capable enough GPU, so then network doesn't make sense to designing that kind of network. So in this section, they completely look into that factor. Given a depth scaling factor, width scaling factor, and resolution, is my target, whatever the target that target memory that they're talking about, or flops that they're talking about, is current system take that load. So that is what this third third equation says about. But overall, what they have come up is when depth equal to something, this kind of factors that they found, and that I think they have done kind of free kind of a what do you say, predefined parameters here. So that those predefined parameters they have assigned, which by default they might work. But in case if we have, in case if we have a high capability, high resources in our machines, then we can increase those kind of parameters. So, but they have come up something called if you increase this parameter, what is the flops? How the ratio of the flops will increase. So those ratios, all those things come on the they have come up in this section. So this complete section talks about the association between the scaling factors that you give and the resources that you have in terms of the session. In terms of the system. So this is completely compound scaling method. So here, one observation that they made is how to add the scaling factor in terms of the 3 dimensions, which is width, depth, and resolution. The third one is given in order to pursue a better accuracy and efficiency, how to balance dimensions of the network. So those are the 2 things that they have come up so far. So once they have come up this one, they need to have some kind of baseline architecture that they have shown in the figure 2 on the above. Actually, the figure that we have shown above. So this network architecture completely designed using the kind of, it looks to me MNSNet based actually. So other than that, here if you see, I think most of the guys are familiar with the these two things. One is inverted mobile and the bottleneck can be the block, and the other one is squeeze and excitation optimization block. So these 2 things they fuse and they created one block based on the parameters that we pass. So here one block they have designed this using these 2 combinations, and here again mobile inverted MB block, if you see, it has got both convolution, fully convolution, and depth-wise convolution. So here if you see the architecture used all the better approaches so far in the literature. They have used a fully convolutional network, and they have used the depth-wise convolutional network. They have used this squeeze and excitation, and excitation ratio that those guys they mentioned they have seen benefit because of this ratio. So I feel like whatever the best possible in the literature, they have used all those things and created one block. So which is nothing. This is the kind of base block that this is in the table 1. So this, if you see each block, it is a mix up of MB block and SE kind of block. So together they created one block. So such blocks we can increase based on the scaling factor that we give. So maybe I think here I can show kind of implementation, high level implementation that maybe when we look into implementation we might get a better idea rather than if I talk something, I mean, rather than talking more on it. So I think that should be fine. Shall I go ahead?
Yeah, can you increase the
Font?
yes?
I don't know. How will I do it? Okay, 1 minute. Is this fine?
Yeah, that's better.
Maybe if you can somehow get rid of the left pane. Yeah. Perfect.
Okay, here if you see this, this is where architecture starts. These two nothing but the initializer for convolutional layer, and this is initializer for a dense layer. I mean, initializer in the sense, as we start this EfficientNet guys, they don't use the transfer. I mean, ImageNet weights. They start from the beginning. I mean, they take the random weights and start it. So while taking random weights, they use the variance scaling approach. So in terms of the convolution, they initialize with this, and in terms of the dense, they use this. I mean, this kind of values. So then next stuff is this is where the compound scaling factor or comes into the picture. Here, if you see the kernel size, they keep changing. I mean, this is how the blocks by default, these many blocks will be there. So in each block, they predefine. I mean, they define the kernel size, a number of repetitions, and input filters, output filters. I mean, expand ratio, ID skip, strides, and SE ratio. SE ratio in the sense squeeze and excitation block ratio. So these things by default they give for a base block. So once you build this base block, I mean, if you pass width, height, and resolution anyway, you need to pass width, height. Just give me a second. Issue. Yeah, I'm sorry. This once you give, I mean, depth is 1 and width is 1. This default block, I mean, default blocks are going to be used. If you use, I mean, I'm going to explain that a bit later, but here I want to say this is the number of, these are the number of blocks, and each block it is going to use this kernel size and number of repetitions. I mean, it is predefined. First block is 1, second block is 2, a number of input filters are this, and output filters are this. Then so I just built something here to see how when you pass a width coefficient. See, for example, if I pass 1, it is not going to change. If I pass 4.3, that means it is going to multiply my initial input filter 32 into 4.3. So it is going to give 136 to me. So this width coefficient is getting multiplied with the default input the filters. Again, a depth coefficient in the sense, depth coefficient is the one which decides the number of layers. Number of layers. I mean, it is going to a number of blocks it is going to add. So how number of blocks it is going to add is, say here this is the one single block. So as they mentioned, here this is one single MB block. So in this block, if you see, are we going to consider the squeeze and excitation block that here it decides? Then this is this is nothing but access deciding, and the dropout factor that we get here from this. Then if you see here, assume this expand ratio is not equal to 1, then first convolution layer with filters that we have got above. I mean, from block arguments, it takes the filters, then batch normalization activation, then on this it ups the depth-wise convolution 2D. Then again batch normalization activation by default they use the switch here. Then if we say has a CE block should be present, then this will be enabled, and the squeeze and excitation block, this is the one. And at the end, they apply again the squeeze. After squeeze and excitation block, they apply the convolution to the convolution layer. So on batch normalization, then if dropout, we say if dropout is required, then dropout will be. So this is the one complete block. So this block, we need to now design how many such blocks we need to have to build a complete architecture. So this is one block. How many such blocks we need to, that is based on the depth. See, for example, I'm sorry. So this is first initial layers, then the block arguments. By default, if you give one, that is not going to change. If you increase the number of blocks, then this will iterate those many number of, this will create those many number of blocks. So this is a default, one block will come. This number of repetitions will say at first stage how many number of blocks. If it is greater than one, so those many blocks will be created and sub blocks will be created. Then convolution layer will be followed by convolution layer. So this is for just last classification. Just to give you here, this is one block where you see this is one complete block, and then the block 1A starts. If you give number of repetitions, number of repetitions, if it is greater than 1, this 1A will come. Then again 1B, based on the number of repetitions will come, those many blocks will be created. So 1C, 1C, etc. So here I have given, I think I have given say 4.3, 5.3 width coefficient and depth coefficient. If I change it to 1, 1, so those many sub blocks will not come. So based on these coefficients, it will increase a number of blocks present in the network, and the resolution we should fix it based on the version that we are using. Each version, if you see, that is fixed. Resolution is fixed. I'll just show you that part as well. It is not my own implementation. I have used it from. I'll show you that reference also. So this is just to show the different versions. B0, if you see here, width coefficient is 1.0, depth coefficient is 1.0, resolution is 220/4, and the next one parameter is a dropout ratio. Next one is this is B1, where we change the depth coefficient and resolution, and dropout ratio remains same. And the B2, we change both the width and the depth and resolution and dropout. So like this, you can keep experiment and see which one gives benefit to you. So that is how they have built. I think almost now, if you see 9 to 10 versions, they have built efficient net. So they're just increasing the width and depth and resolution, and they change and they see the benefit out of it. So that is a bit of architecture and about compound scaling factors. Then again, we will pause here and see if we have any questions, or if we have anything that we need to look into further. Yeah.
Just to add, Viru, like depth, like you said, is layers. Width is kind of a weird terminology here because we are kind of used to thinking of height and width of images. So
yeah.
Right. Yeah.
Yeah. So yeah, no, I'm not talking about width and height of images here completely. Depth is nothing but the network depth. Width is nothing but the number of neurons in each layer.
Right, neurons, or you can think of like number of channels in each layer.
Yeah. That's yeah.
One more point to add was that from my understanding, when I read the paper, was kind of like when you do this NAS, you're basically using AutoML. So you basically set up this base network, which is B0, and shove that to AutoML and tell it search. And you're doing that on a smaller network, so your search space is smaller, so you'll be able to search faster. Once you search and get your parameters, then you already have those two formulas where you have like alpha into beta square into gamma square should be equal to 2. So then you can kind of go ahead and tweak and make bigger architectures without using NAS for that, right? That without using NAS power, right?
Yeah, but as you said, you're absolutely right. As you said, first we need to use NASnet to build the base network. Once you build the base network, as I mean here, as I highlighted yellow, these two steps will execute to build the next versions of the network.
Okay, right. Okay, cool.
Yeah. So this is, I mean, if we, for me, I mean, I cannot say I'm 100% sure. I mean, 100% confident on this. It is because it has got lots of dependencies. So entire neural network architecture, I mean, NS, I mean, AutoML framework, we need to understand. I mean, how this exactly built up to give the questions for these parameters. Again, I mean, alpha, beta, gamma that they have come up. They have initialized. I mean, as I shown here, they have initialized some predefined values. So what will happen if I change this one? This they might have come and they might have got from AutoML framework. These parameters, initial base network parameters. So I think we need to have a good understanding on the AutoML framework, then ResNet, then squeeze excitation network, then gpipe, and wide resolution networks. So all the references that they have pointed out here, if we have some kind of good understanding, then we kind of get good intuition of this paper. So that's what I mean. I was digging. I mean, I could see lots of papers referred there. So
just one more point that I was reading was that you have this alpha, beta square, gamma square, and I was wondering why that is not an alpha square. And basically,
that I did not mention. I'm sorry about it, but they have mentioned somewhere here. The alpha square, I mean gamma square. It is because if you double the network, here they mentioned. I think I mean I just ignored that part. They have mentioned here doubling the network depth will double flops, but doubling a network width and resolution will increase the flops by 4 times. So that is the reason they made it alpha for depth. So beta square for W width and gamma square for resolution. So I think that is the point that you want to mention.
Yes.
Yeah. So I mean, intuition is clear. I mean, clear in the sense if you increase a depth, so the way it increases the flops is for, I mean, going forward for one layer. But if you increase the width, the flops will be increased for both input and output. So that is the reason it increases 4 times. So I mean, it happens same thing to the resolution also. So yeah, I was I was just checking for the same thing. I have a reference here. I mean, the Reddit. This is where I found same thing, same logic. What we are talking about here. The simple example is if you take a dense layer. So if you build a 4x4, it needs 16 weights. But if you make it 8x8, it needs 64. So and that dense layer we can take as example for that. So yeah, I think. Yeah, that's a good point. I thought of mentioning, but I forgot it actually. Yeah.
One more question with the code where you were sharing that 72 when you changed it to 4.3, right? I kind of lost. So does that mean the block gets repeated like 72 times? Or what is
this is output filters actually.
Oh, okay. Output filters.
The first one is input filters. Then the second one is output filters. The third one is number of repetitions the block needs to repeat those many number of times.
That makes sense. Okay. Yeah, that 72 as block repeat sounded too big, but yeah, that makes sense.
Yeah. So yeah.
Sorry, one question there again.
Yeah.
The first one you starting 136 and going to 72. Are we like reducing the number of blocks on that one? I mean, sorry, reducing the number of output filters on that. Everything else seems to be increasing, right?
So even output filters also getting increased, right?
No, I'm saying usually whenever you build, output filters is always greater than number of input filters, right?
Okay, yeah, that's true.
I don't
Yeah.
know what is happening. Interesting. Okay. Is 4.3, 5.3 something you set, or is that one of the EBs?
Yeah, no, it is not. I said it is. I have taken from this guy.
Okay, so it's one of the
So if you
predefined.
see, yeah, you see. I mean, as I shown, I mean, here I have shown it is because each version it changes these factors.
Right. Okay.
So yeah, I mean, I just took 2 samples from this and try to explore. I mean, what is happening in this board. So that's how I initialized it. So yeah, so that is more or less about the whole paper. But next section, it is kind of experiments that they have done. Those are also looks promising to me. It is because I mean, people general ideas or ideal thinking that we get is what happens if you apply these scaling factors already designed networks, something like mobile nets or REST nets, or any squeeze and excitation network, anything that you take, just apply this compound scaling factor and see how the behavior, I mean, how that behaves. So that is the first part that they have done, and the results seems quite good. I mean, compared to the base network, this is the table 3 shows the results. So if you see the compound scaling factor, using this compound scaling factor, how much benefit that they got, I mean, in terms of the flops, into the accuracy, they have listed in table 3. So even if you use this compound scaling factor with the earlier designed, I mean, earlier design networks, so there also it does quite good. That's what I mean, it does good there. So that is what they showcase here. And this complete or maybe this table, complete table, if you see, it is a kind of a mapping in the sense, ResNet 50 is the one that they can, I mean, at which efficient net B0 also present. I mean, the present in the sense with respect to number of layers and number of parameters, you can take a ResNet is similar as efficient at B0, or DenseNet 169 is similar to B0. But when you see the model accuracy and the efficiency, efficient at B0 wins, I think. And that's kind of comparison that they built in this whole table. So when you see efficient at B7, they have compared against the G pipe, which is a state of art before efficient net. So like that they have done this. This table shows kind of good summary, I mean, what they have achieved using this approach. So this again, the flops versus ImageNet accuracy, I think we have seen earlier at I mean, which is almost figure 1 that we have seen at the beginning of the session. This is the table 4, and I mean, this they talk about inference latency. I mean, when you just run inference, how good it is, the network. That is one part of it. The other part in experimentation is, I mean, if you see how good it is with respect to ImageNet data. So what are the parameters? I mean, what are the optimizers, the parameters that they have set? All those things they talk here. And this table 5 shows something like they have taken basically different data sets here. So almost 7 to 8 data sets they have taken, and they have compared against the different versions of the public available results. I mean, NASNet, Inception, and ResNet, and they have publicly some accuracy, some number of parameters that they have shown in these papers, that they have compared against those number of those things. Then the comparison to best reported results, I mean, best in the literature that they have compared. So here also it is efficient net wins. And this, if you see this kind of picture, it talks about the different data set, how I mean, model parameters transfer. Here basically they have done transfer learning in the second section. With respect to transfer learning, and what is the number of parameters and the accuracy that they have plotted here. This red plot is nothing but in the efficient net, and they have given each symbol for each network that they have used. So that is something in terms of the transfer learning, when they apply transfer learning, mostly they talk something in terms of the flops, in terms of the memory, in terms of the accuracy, how much benefit they got, and what they have used here. This is, as I mentioned, Swiss activation function that they have used, and I mean, there are different things that they have used. I mean, dropout rate, or how they linearly they increase it from 0.205. So all those things they talk here, and this activation kind of maps showcase differentiation between scaling, compound scaling, and individually, if you apply a deeper models, wider models, high resolution, how they behave. So this is kind of clear cut. I mean, clear cut result shows that compound scaling wins against the trying individually each tip. I mean, each one. And the third thing that they have done is transfer learning results and for efficient net. Yeah. So this is kind of result section that they have given. I mean, that they have done comparison with existing state of the art results, and showcasing different metrics and activation maps, all those things that they have done in this result section. So with that, more or less, I have done with the paper. Yeah.
Yeah, quick. So they pretty much equated subsequently memory size which they originally stated to the number of parameters then because that's the only relation to the original objective of having something less than a given memory. They just make it the parameter size.
Yeah, I think so. I mean, in terms of, flops. I mean, in terms of the flops, if you see, right, this is very much less compared to the existing state of art. Right? I mean, GPipe, for example, if you compare GPipe, and yeah, I mean, I think memory they might have done with that only.
Yeah, if you actually go back to the table, they don't even mention like GPipe's flops, right? If you scroll.
So here, I think this is
one more. Here, one more above. I think I was just seeing that.
Here, the number of parameters that they talk, and the accuracy that they talk here in this table. Yeah, here.
The complete table. Yeah, this one.
Yeah.
Last row.
Yeah, last row shows the. Yeah, that's true. So yeah.
So with CIFAR 10 and those data sets, when they are playing with and perform these experiments, CIFAR, I think, is like pretty small, right? 32 by 32 or some resolution.
Yeah, that's true.
So with EfficientNet, you have a predefined size that you need to stick to, like B0. I forgot what the size is. So do they just
224 it is.
Oh, okay. Yeah. So they just scale that 32 by 32 up to 224 by 224 for this experiment?
I think so, but I am not sure if I come across something like that. I mean, with respect to resolution, whether they have scaled up or they have applied the same resolution.
So when you do transfer learning, what do you do? Let's say, because you have to kind of compare, you have to be compatible with whatever these guys you're using, right?
Yeah. When we have to, when we apply transfer learning, we will have to scale up, right? We cannot apply the different resolution.
Right. Okay.
Yeah, that's true. Yeah, I think I'm a bit out of time, but lastly, I want to show, I just need 2 minutes. I want to show some important references which might be useful if somebody wants to use it. This is, I have been referring this since sometime, I think 1 year, I think now. This is really good site where they have implemented everything in a TPU, but people started porting that into the kind of TF Keras or Keras. So this also can be used, but here the only thing that I want to highlight is, so if you see May 2019, this is the base network, efficient network, BaseNet, and it has got 7 versions in it. On top of that, they have applied the augment, auto augment, which give, which boosted the accuracy further. Then this edge TPU kind of for mobile models, something like that. Then they have applied random augment, which is kind of given again the accuracy boost. And the major this thing is now the state of art is something like noisy student, which is a kind of a semi-supervised learning. I mean, it's a kind of teacher-student model that they do in noisy student, if I'm right. I think so, if I remember correctly. I have had a look into that paper some time ago. So noisy student, when the advantage with the noisy student is nothing they have changed other than feeding the more data. So they have fed lots of data. I think more than 300 million data something from YouTube or something they have downloaded, and they fed that, I mean, that those many samples to the network, and it is generalized well. That is the only thing that they have done. But the way they have done is it is a kind of the student teacher. I mean, you run once and it gives some false negatives. You correct them again, run it, and then this is a kind of semi-supervised learning that they have applied. This is the accuracy. I mean, once you from baseline to noisy student, how the progressively they have improved the accuracy. I think which is kind of a good to mention, a good place in improving the accuracy. So is, I mean, good reference to know each and everything from the efficient net point of view. Yeah, I think I'm done. I'm 6 minutes ahead of my time.
Thanks, Viru. Yeah, can you put that link for TensorFlow in the chat?
Yeah, I will share. I will share
Okay.
these resources in the Slack channel.
Okay, thanks.
Yeah, thanks for giving me this opportunity. I will pass it to Mehal. Mehal, is it correct pronunciation?
Yeah, that's
Okay.
good. Okay. Yeah. So the way we decided is, yeah. So thanks for that great overview on EfficientNet. So originally I was going to talk about RetinaNet. RetinaNet is a type of object detector, and I thought I should give an overview of object detection. So let me share my screen. Okay, do you see my screen?
Yes.
Okay, so far, the book chapter we covered, we mostly, we focused on classification, and we various architectures to do classification, and then like we will just talk about efficient nets. Okay, so this, so my so what I'm going to talk about for the next hour or so is basically this category of object detection, and some of the challenges in object detection and how it compares to classification. Okay, so basically, so far classification is like, yeah, you have 1,000 ImageNet categories. Okay, what class is it? But now uh, what we care about is putting not only saying what class it is, but where it is in the image. Okay, so you can think of a number of applications where this is very useful. So for example, self-driving cars, like in the self-driving car example, okay, where are the other cars in the image? Or in the medical perspective, let's say you have an X-ray, and you just don't want to say, is it like is there cancer or not cancer, but where is the cancer? Okay. Oh, and these are these slides are these. I was looking for material, and this is from the University of Michigan. Um, some of you might be familiar with this name, Justin Johnson. So he's part of the original CS 231, and now he's himself he's a professor at Michigan, and these were from like about a year ago. And the reason I picked this is there is his lectures from November 2019 are on YouTube, so you can listen to the slides, and you can listen to the lecture and see the slides at the same time. Okay. Okay, so our for our task definition, we have a single image, and we want to our goal is to find the detected objects and give the we want to know what category it is, and we also have to give the bounding box, which basically is defined by 4 numbers. So it's okay, maybe where it starts, so x and y, and then the width and the height of the box, right? So these 4 numbers completely define the location. Okay. So there are a couple of so I think we'll he does a really nice job of comparing to classification, you know, like, so in the past, so okay, here we need to uh, we have multiple outputs per image, and we want to do what and where, like I mentioned. And so most of these images, object detection is done on bigger size images, so in the range of around 800 to 600. Okay. uh, so let's say let's take the simple task. So here we are doing multiple objects, but let's start with, let's say you just had to detect one object in the class, right? So you could just have the traditional classification we saw so far, to say what is in the image, and then uh, to predict the location, you since you have to detect 4 values, like the 4 coordinates, you consider this as a regression problem. Okay. And now your ground truth has the correct positions too, right? So if you have your predicted coordinates and the actual position of the box, you can measure, and you can measure some loss. So here he talks about a L2 loss. um, and then find, but now because we have the what and the where, so you have to combine these 2 losses, and here he just does some weighted sum of these 2 losses. So then you try to minimize the weighted loss. And yeah, many times this part is uh, is just the it's just the like from transfer learning is a network that is just pre-trained. So sorry, one thing I didn't mention here is, you know, for the classification part, we went from like 4096, so that's the fully connected layer, to 1000, because there are, let's say, you know, like just say 1000 categories. um, but for the regression box, we are going to go from 4096 to 4. Okay, that's the idea. Yeah, and of course, in yeah, this is a toy example with a single object, but in real life, you could have multiple objects, right? um, so one, if you if you try to extend this approach to multiple objects, you run into the problem that um, you you know, for, so say you have three objects, you know, then he made a typo here, so then you have to predict uh, 12 numbers, and like here there's a bunch of ducks, so um, uh, you know, you have to predict many different outputs per image. So what people did for multiple objects is, so one way you could do multiple objects is have a sliding window, right? So you crop an image, and then you go back to traditional CNN that we learned, you know, that we've just been talking about, and you just say, okay, there's a dog, cat, or you say background, you just add a background class. um, but you immediately run into number of issues here. um, yeah, you're going to uh, you know, if you try the sliding approach, so how many how many possible times are you going to do this? So let's say your image was of size capital H by W, and if you consider a small box of a box of size small h times W, you could place this box in so many different locations in this image, right? And these are all the possible positions, right? That this box could be, and then you would have to make so many classifications. But of course, the problem is harder than that. Here we are assuming a fixed box size, but you also need to consider boxes of all possible sizes, and then if you so all possible sizes, all possible positions, it comes out to this. Okay. So it's and then for every box you have to run your classification, which is it's just very computationally intensive. Yeah, okay. So there you go. Like, so if you have a 800 by 600 image, you would have 58 million boxes, and there's no way, yeah, and that's just for one image, right? Uh, okay, so this because you have classification, but object detection is a very important task in computer vision too. So one idea researchers came up with is, let's not do like all these 58 million boxes. Let's have region proposals. Okay, so this is a term you will find across like implementations and papers. So when they first when this idea first came, they used um, a traditional image processing non-deep learning based method, which would give like say in the range of say 2000 region proposals. Okay, so if this was your image, these are the region proposals that were given, and this is by some algorithm called selective search. Okay, yeah, I don't have I don't even know it, and I think it's just good to know, but pretty much nowadays no one is using this approach. But this is how object detection kind of matured to where we are. So I thought I'll just talk about a little bit about how how it was done in the past. Okay, so you would have region proposals, like these 2000 region proposals, and the first multi-object detection method was called Rcnn. So the way it worked was, you have the input image, you get your region of proposals, region of interest proposals from some method, right? Like the selective search. They resized everything into boxes of images of size 224 by 224, and now you run these 2000 images through a convnet. Okay, and we still we still have to do two tasks, right? We have to say what and where. So you at the end of this convert, you predict the class, and you also have um, you also want to predict the bounding box. Okay, um, so one thing um, in why he talks about correcting the ROI is that the initial region of interest might not exactly be in the right position, right? It might be shifted by a little bit. So if you want to correct a region, so in this case the regression is used to correct the- your initial ROI. Okay. Um, so for example, let's say you initially, when you had the proposal, you had px, py, ph, and pw. So it's x and y, height and width. Okay, and the in the regression, we try to have tx, ty, th, tw, and basically the final where is the output box, which is based on bx, by, ph, bw, and it's uh, there is some equation here that was implemented in the paper. The Okay, so basically, I didn't follow the log scale, but maybe I'll try to put a link to this part of it. Um, yeah. Okay. So now this is during training time, right? And then during test time, you would have to do this again. You would basically generate 2,000 proposals on the test image, um, resize them, pass them through the convolution network, and get like a bounding box, get the final bounding box and the class. Okay, so one problem of this compared to classification was where we could, okay, we know did we get the correct category or not. Now we also have the bounding box. We need to see the performance of how well we did. So uh, now here is where we introduce a new metric to see how well we gave the bounding box. So the metric that is introduced is called intersection over union. It's pretty intuitive. So basically, let's say the blue is our prediction, okay, and the green is the ground truth. It's simply the area of intersection. So in the middle, this orange part divided by the area of the union, right? So for example, if you had a perfect, if you predicted the location perfectly, you would have an IOU of 1. Um, and yeah, and if you had 0 overlap, your IOU would be 0. So IOU ranges from 0 to 1. And if you from people have defined ranges. So what is a good IOU? So if you get an intersection over union of 0.5, that is considered a decent IOU. And if you get something like 0.7, that is pretty good.
That area of union is kind of weirdly marked, though, right? In the previous image, doesn't the purple cross over the top right corner and the bottom right
Yeah,
corner? Those shouldn't be there.
yeah, this shouldn't. Yeah, probably he has a typo. Yeah, or he didn't. Yeah, that's yeah. Yeah, you're right. I thought it'll just be this, right?
Right.
The
It should
two.
just be individual box areas minus the intersection kind of gives you that. So that should not be there.
Um, individual box
Yeah, the
areas.
diagonal purple areas, right? Because the
Yeah,
green
this.
Right.
one would be there. Yeah, that one and the one on the left
Right.
bottom.
Yeah.
Right.
Yeah. Yeah. I think maybe he's making a. Yeah. I think it's a type. Yeah, that looks like a typo there. Yeah, like
But
a.
I don't understand how you get a union without that.
Union there otherwise will be, if you just look at the blue box, you calculate the area that that blue box occupied. Look at the
Okay.
green box, calculate the area that the green box occupied, and then you subtract your intersection because you've twice added intersection in, right?
No, yeah, intersection is fine. Union, okay, union we can calculate the area of two boxes and sum them up. Then that is a union. That's what
No,
you're
no.
saying.
If you sum them up, you're adding intersection in twice, right? So you have to subtract one intersection out.
Right.
Yeah, yeah.
Okay. So then, like if you do this in practice, it's very hard to get a IOU. If you get something like 0.91, it's really great, but in practice we don't see those values that often. Okay. So okay, we have the what and the where, and that's the metric to compute your result. Uh, any questions so far? Okay, I'll proceed then. There is another unique problem that comes with these object detection methods is uh, you might get uh, multiple boxes. So in this case, for the dog on the left, you have a blue box and you have an orange box. So the blue box, let's say he just gave that probably 0.9, and um, with the orange box that it's a probability of a dog is 0.8. Okay, so but in the end, you just care about you just want one box per object. Okay, so what object detection method introduced is something called non-max suppression. So you basically um, let's see if I can remember non-max suppression. It's basically a method to eliminate like duplicate overlapping boxes, and so that in the end you only have one box remaining per object. I don't know if anybody else has a intuitive explanation for NMS.
I think you just calculate IOU for all those overlapping boxes that you have.
Right. Mm-hmm.
And then you just keep dropping the lowest one, I think.
The lowest one.
Right.
That's right.
Just keep the one with the highest IOU that you have. I think that's pretty much it. And then they have some thresholding of, like he's mentioned, 0.5 or 0.7.
Yeah. Yeah. And
Right. So I think if we look at that figure that you have there,
mm-hmm.
it says IOU of blue with the orange is 0.78, where blue is the ground truth, right?
Mm-hmm.
And blue with the purple is 0.05 because, yeah, that's like marking the other dog altogether. And blue with the yellow is again marking the other.
It's not the ground truth. It's so, the algorithm made all these outputs.
No, but the blue box, I think, is the ground truth box, right?
Oh, I see. Okay, I see.
Because that's why you're comparing everything with that on the left-hand side with IOU. Like the bottom figure that you have where you just, yeah, that one. That is, yeah, that's what I kind of remember at the top of my head now.
Is he doing two ground truths? Because when you flip through the slides, it went to 0.752. So he's doing one for the left dog, one for the right dog.
Right,
and then
right.
Going through and then doing what Rekil said.
For each of them, yeah, you need to do.
Yeah, for each of them.
For each box.
Yep.
Okay. And one, okay, so this, this works well when you have objects that are like well separated. And one open problem in the research is, like, suppose you had a lot of, it's like a very densely packed image, like this one, um, where you have multiple objects, so many objects. And here people have noted that this NMS approach might uh, eliminate some good boxes, and at least like there's not been like a very good solution so far, right? Maybe you're doing maybe in an airport security application, right? You have so many images, and there's like, if you have a lot of people, it might be hard to like say detect where mm, if you have a dense image like this. Okay, so okay, so this was, so we had, so he introduced a couple of concepts. So first was IOU for object detection, then NMS for suppressing overlapping boxes, so you have only one prediction. One other complication that comes up with object detection is now measuring the performance. And so there is basically all the papers use mean average precision, but his, like in the this is kind of the best walkthrough of MAP I have seen. very clearly describes all the steps. Like some of the papers, when you read the papers, they don't describe all the intermediate steps, all the steps involved in computing the MAP. And I'll try to go through them. So you basically let's consider one category, right? So you have all the dog detections. Let's say we only consider about the dog category. So these are all the dog detections sorted by score, and these are all the ground truth dog boxes. So now for basically you okay, so whichever is the highest detection, you try to see match. Let's take you consider an IOU of 0.5, and you find which of the ground truth matches with that particular detection. So in this case, let's say 0.99 matches with 1. Okay. And then you say, okay, so this ground truth is taken for. Okay. And what you do is for each of these, you for each point, you create this precision and recall graph. So here what we had is um, our precision was 1 because we detected with that prediction, we detected one. It was like, yeah, we had one prediction and one detection. So one by one. Okay, and the recall is we got one out of the 3 ground truth boxes. Okay, let me show you one more point, and that will help me. So now, um, okay, so we have two predictions, and we were able to get 2 ground truth boxes. So we got 2 by 2, and then the recall is 2 out of 3. Okay, and then you get a second point on this graph. Let's say for this prediction, there is no ground truth was found. So now we have precision becomes 2 by 3, and recall is 2 by 3. So it's this point on the graph. And let's say this is also an error. And yeah, so you get your next point. And lastly, okay, so now we've got all the points on this curve. And so the average precision for the dog category is basically this area under this curve. Okay, so so the average precision is the area under the PR curve. Okay, so we have done this for one category, but you might have multiple categories. So you would do this for every category that you care about. Yeah. Okay, so you would have like a car average precision, cat average precision, and dog average precision. And the paper will report like something like, okay, and then you take the mean across your categories, and so now you have a mean average precision at an IOU of 0.5. Okay. So any questions so far?
That is, I think, at an IOU of greater than equal to 0.5.
Right. Yeah. Thanks. Yep. At or greater than 0.5. Yep. And so then it becomes, so you see the evaluation is becoming harder and harder, right? Like now you not only, so we just picked IOU greater than 0.5 arbitrarily. So now you need to consider at different IOUs. So 0.5, 0.55, and if you if you make your IOU higher, so at you can imagine at an IOU of 0.95, you would have a much lower average precision. So this is just showing that trend. And when you look at like an object detection paper, or like a or just some implementation, they will typically give tell give a MAP. So mean average precision is the final number is basically an average of the mean average precision at different IOUs.
That's the COCO map, though, right? Because map is just the mean precision at a given IOU of all the classes. And COCO map is the one that he says yet another average of MAP applied across IOUs.
Right. Yeah, that's true. So that's how the COCO is like a famous data set. I'm thinking if other wonder if what's going on in other object detection. Like if I do my
like CAMVID or something.
CAMVID, yeah. Okay, so this, and I think modern, like up to 2019, like the final number was around like 0.35, 0.4. So it's, that's been the like state of the art around 2017, where you get a map of 0.4, and some recent methods have increased it to 0.5, 0.55, and we will come to those.
So I think,
yeah, go ahead.
no, just saying, COCO map is basically start with all IOU starting from 0.5 up to 0.95, increment by 0.05, calculate the maps for all those, and then you take average.
Oh, so you're saying we could have done like maps at 0.5 instead of incrementing at 0.5, 0.05, we could have incremented at 0.1. Right?
No, no, that's what I'm saying. COCO map is specifically like 0.5, 0.55, 0.6, 0.65, all the way up to 0.95, and then you average it. It technically really has nothing to do with COCO, though. It was just performed first with COCO, I guess.
I see.
It's just that any time you perform it, like you get a new data set and you want to compare it, you do like map at 0.5, that will be one metric. And then if you want to report COCO map, then you have to do map at 0.5, 0.5, 5.6, all the way to 0.95, and then average that and report that.
It's the kind of the average of the maps across the IOUs at that step, at steps of 0.05 starting from 0.5.
Right. So suppose we came up with our own object detection and we wanted to compare to other previous work. Yeah, we on the COCO data set, then we would have to do it this way. Right?
No, but what Raquel is saying is it's a metric which is independent of COCO. At least that's what I understood what Raquel was saying to me. So you could say, for example, that for CAMVID, your COCO map metric is X, and that would imply that you have done map at all IOUs starting from 0.5 up to 0.95 in increments of 0.05 and taken the average.
Yeah, okay, makes sense. Okay, so compared to like our classification, so we have three new things. We had the IOU, we had non-max suppression, IOU, and then now mean average precision. Okay. So these were the three things introduced to measure the performance of object detection. One second, what was? Yeah. So in the original method that we had, the problem with this is very slow, because you start with 2000 proposals, and you have to do forward passes for like 2000 times. So when they I guess they got So the first method was Rcnn. So the next method was called fast, was just called fast Rcnn, and all they did was they swapped the order. So instead of running the region proposal first and then running the convnet, they're like, let's just run one convnet. So this is a convolution network with no fully connected layers, just convolutional layers, and this is typically like referred to as a backbone in object detection. So in this case, the backbone network could be anything that we have, that we have already gone through, like AlexNet, ResNet, and I think some people also started using. I don't know if somebody's already tried EfficientNet as a backbone, but
Yeah, lots of people, I mean, YOLO, SSD,
okay.
they're almost all the object detection techniques they have tried using efficient.
Okay. So now you have the convnet and you have your image features, and you basically run your uh, proposal on the output of the convolution neural network. Okay, and what you still need to do the classification part, like the what part. So here they have a simple, very lightweight CNN, and we'll see the uh, difference in like performance between these two methods. Okay, so so like conceptually the main switch was between the convnet and the ROI proposal. Yeah, he just talks about that. Yeah, this is lightweight, and this you just do the computation once in the backbone. So this saves a lot of this is where you get your uh, where you make some gains in performance. So for example, um,
Sorry, Mayul,
yeah,
does he refer to that as a switch between fast RCNN and RCNN? Like, is he talking? Does he explicitly say that, like, convenience apply it right at the beginning, and that's a switch from slow RCNN?
yeah. So basically, yeah, that's what he just compares it like this.
I see.
Yeah.
My understanding was that in slow RCNN, you basically use a non-deep learning approach at the first step.
Yeah, to find out the 2000 bounding box that he spoke about, he doesn't use the CNNs.
Yeah, no
Right,
CNN.
but even here it's the same. So here you found the bounding box on the image. You still use the same same non-deep learning method, but only on the convolution features. So it's the same ROI method. That method didn't change yet. So that's in the third. So there is a
Oh,
third
I see.
algorithm. Yeah, there is a
Okay.
third algorithm called faster RCNN, where even the region proposal is replaced by a CNN.
Ah, I see. Okay.
Uh,
Cool.
So you have selective search here, but now he said I just do selective search here instead of doing it on the image directly. Yeah.
Okay.
Okay. He talks. There's some. You get into some hairy details here about um, how to because now you're in you are in the CNN feature space. So there's some details. I'll skip this part. So they came up with a method called ROI align. Okay. Yeah, so basically, yeah, that's what the summary was. Yeah, this was our proposal method, like selective search here, and then here, this is the same selective search method. And this, um, this is what happened with when you compare the fast RCNN and the slow RCNN. So the slow RCNN, that time, this is a little bit the older GPUs, but around 2015 it was 84 hours. But with that switch, they were able to reduce the training time from 84 hours to almost like 9 hours. And of course, you get a much bigger uh, improvement at test time. So in the RCNN was, yeah, say like for 49 seconds, 47 seconds, and fast RCNN becomes even yeah, you get a much bigger improvement at test time. And what the blue and the red is, so the blue is the non deep learning based region proposal, and red is okay, what all of the CNN and all the deep learning stuff. So they immediately you notice that most of the time in fast RCNN is wasted on like the region proposal part. The region proposal part is 2.3 seconds, and the CNN part is only 0.3 seconds. I guess they didn't. I don't know. Maybe they didn't have creative names. So um, is okay. So so far we are doing region proposals with selective search. So now why don't we have a CNN? Uh, learn them with a CNN and not rely on traditional image processing methods. And so that that method is called faster RCNN. Okay, so this is basically where the idea of learnable region proposals was introduced, and they introduced like a region proposal network. Um, so now um, so here these two steps are similar. So between fast and faster RCNN, the first two steps are similar. What was included, what is new in faster RCNN is that for you try to say this region proposal network tries to say two things like, is this is my proposal like is it something of interest, like should I keep it or not keep it, should I pass this proposal to the next layer or not. And the same thing, so okay, I have am I going to keep this region to be passed on to the no? So it becomes a binary classification. And the same thing, you still have like a bounding box uh, or regression loss. There's some, yeah. And then the next stage is where you do actually classify into all the classes, and you have you need to predict again the bounding box for the object. So now you start having four different losses for this work. Okay, it's running out of time a little bit. I'll come back. So this kind of gives you the summary of what of the four losses for the fastest RCNN. Okay, so you say, okay, is the anchor box, is there an object or not in object or not? So this is RPN just stands for region proposal network. And it's when you started, when the RPN started, they had something called an anchor box. So okay, you need something to start with. So for example, uh, these are some typical anchor boxes in blue that you see here. So you would need anchor boxes of different sizes and different scales. Okay. Yeah, and of course, like when you start, you don't know in the region proposal network, you wouldn't know the um, right size and shape. Right? So the idea was, okay, use different anchor boxes at each point.
Is that ROI pooling happening there so that you kind of look at different resolutions? So you kind of take care of different box sizes?
Yeah, exactly. So you want to they picked. I think you still have to pick some
Fixed anchor box sizes.
right. Yeah.
Right. Yeah.
So I let me see. I think I had when I did this. Let me see if I have an example for you. It's not exactly. Oops, sorry. It's my GitHub. No, not that. Let me see. Okay. How do I get? Yeah, got it. Thank you. So this is it's this is also another type of object detection, but it had little more. So you can pick things like um, like you might pick a ratio, like okay, like do I want a value of 1 means like I have a square anchor, a value of 2 might mean like I have like a more vertical anchor or a horizontal anchor. Okay, so this RPN anchor ratios, this idea extends to even other methods after fast Rcnn. And what you see here is like they all I'm showing is there were a couple of us. We were all using the same method for object detection, and there were like different parameters to choose while doing object detection. So I think here, so we talked about the backbone. So some of us used different backbones. RPN turned out we all just ended up picking the same RPNs. Here, yeah. So Rekil, what you were saying, like you want to get because you don't know the scale of your object beforehand, right? So you might try different scales for your anchor boxes.
Right. Yeah.
Yeah, and when they introduced this RPN this RPN idea in 2015, then your test time performance went from 49 seconds to 0.2 seconds, which was like I think in within a year, like 2014 2015, we made these big improvements. And so then this method, this RPN idea has stuck around for some of the newer uh, sticks around for some newer methods like mask Rcnn. Yeah, and okay, this was another key summary that I wanted to point out was so these methods like fast Rcnn, fast Rcnn are called two-stage object detectors. So um, in the first stage, you run this once per image, right? You have some backbone, so this is your backbone, and you have a region proposal network. So basically, at the end of this stage one, you get let's say you get some region proposals which or areas of interest, right, where you think there may be an car or there may be and like a different object possible. So and that, say, let's say number of, so you can say, maybe you can set that, let's say at the end of stage 1 I want say 300 to 400 region proposals, right? And then I'm going to pass them um to the stage 2, which will say, okay, what is, okay, given a region, what is the potential class, and then try to find the best bounding box. And sometimes even from those 300 regions, you might have regions without any object. So you would maybe you would include a background class. So these are the two-stage detectors. But when you look at the object detection literature, you will hear like single-stage detectors. So YOLO is a single-stage detector. Um, yeah, and so many people, well, the next logical question was, do we really need the second stage, or can we do everything with just one stage in the first stage? Like, you are making a binary classification here. Why not just even make just do the object classification in stage 1 itself? I don't know if someone is yeah, so right, so now you would also do yeah, basically you also classify the object as one of the C categories, and so we still have when we started, we still have K anchors at each position in the image feature map. If I don't know, Viru, of one of you, I haven't looked at YOLO so much, but like do you have some insight about like like when you implement YOLO, uh, like a number of anchors you would typically use, or if anyone has worked with YOLO for and setting the number of anchors? Okay, maybe not. Okay. Yeah, and so what was new was, yeah, you could yeah, so this backbone would remain this, like this is a similar idea of the backbone, and then and this paper kind of summarizes all of our like many of our modern object detection methods. It was they basically implemented most of the object detection methods from scratch, and this graph is very nice for a couple of reasons. Remember, we talked about the backbone, right? So the backbone could be any of the architectures we have studied. It could be a VGG, it could be a ResNet, it could be something lightweight like MobileNet. Um, and there are a couple of interesting things that happen is that when you have a more, if you compare Inception ResNet v2 versus MobileNet, you see the incept if the backbone is Inception, you generally get like a better performance than the if the backbone was MobileNet. And sorry, I forgot to say the y-axis is the overall mean average precision. So this is 2017, so the best at that time was around 37, right? And you also see yeah, the color indicates the backbone, and the shape indicates if it is like a single stage or two stage. um, so for example, yeah, this is a single stage detector versus the circles are all faster Rcnn. And some important takeaways were like uh, you get the best performance with these faster Rcnn's, but then the performance is slower. So maybe if you are doing it on a mobile device, you might prefer a single a single stage detector, because you care about I want to say that, yeah, you care about like how much time it takes. Yeah, then yeah, of course, all the single stage detectors much faster, but map wasn't as good. Um, yeah, I think bigger backbones give you so they improve the performance. And then since then, there have been some tricks, such as one is this idea of feature pyramid networks. So you make some changes in the backbone, and or you have a different backbone like res next. I don't remember. I missed one of the lectures, so I don't know if we talked about this particular architecture. Yeah, and in more recent times, like these methods have improved. Yeah, even the single stage detectors have improved a lot. And this is like very this area is very active. They have a open leaderboard, and I think right now the best method is something like has reached a value. The best leaderboard score is 55, mean average precision of 55. So just in 2 or 3 years, we have jumped from like around 35 mean average precision to 55. Yeah, and it becomes so suppose you need to use it in your work. It becomes, there's just too many steps, like you saw. Like you pick the backbone, and there are I didn't talk about like doing back propagation through the region proposals and through the backbone. So your training becomes a little more complicated, more things to take care of. So um, mostly like the big packages like TensorFlow has a TensorFlow Detection API, and PyTorch has Detectron 2, um, which implements, which will give you an implementation of all the object detection methods, of common object detection methods. I did use this some time ago. This is it's pretty awesome. You can do things like you can see how your objects evolve over time, and how the boxes evolve over time using TensorBoard. I'll try and share a link of what I had done. Yeah, and but this kind of yeah, this is a summary of the methods we talked about. So initially you just had the image. You would have a non deep learning based proposal method, and then pass each of them through convnet and predict the what and the where. Uh, fast fast Rcnn, change that, switch that. So you run the convnet first, and then do your region of proposals, then do your region of interest proposals. And in the modern methods, we uh, we don't use an image processing based method, but we have a like a deep learning method network to predict region proposals. And this was faster Rcnn is a two-stage approach, and lastly the some of the newer methods are just single stage detectors. Um, okay, I think that's it. That's all I have for now. Yeah. And yeah, as we see from this graph, it's very active area of research. So let's see, I think I was thinking about this. You know, it's initially it sounds like 35 or 40 is a low map, but map score, but that's this is the best we can do. Yeah. Okay. I think,
Yeah, like we were saying, the top right guy that you have there with question marks, that's the efficient debt.
oh, efficient debt. I see.
Yeah. That's the 2019, I think late 2019 paper. But they use the ideas of both the things that we looked at today. Efficient compound scaling combined with how you do object detection.
Oh, yeah. Yeah, this is the website he linked to, but yeah, I haven't spent too much time on. Okay. Yeah, and if oh yeah, just last note, these notes are pretty good. So he even has an if you really want to torture yourself, there is an assignment on implementing object detection from scratch. And I think they did a really good job of like setting up things for you. So, but it's an assignment based in PyTorch, and this was lecture 15. But they also have a really nice lecture 8, which summarized everything we did in the book. But the reason I liked his slides a lot was he put it in the historical concept, in the historical context. So for example, when we started with AlexNet, they were initially everybody was like, okay, let's they showed like you had AlexNet, then ZFNet, and then VGGNet showed that you got improvements in performance as you got bigger networks. And then after that, GoogleNet was one of the first to focus on efficiency, so the inception stuff. And so 2012 and 13, 12, and then this was 2014, 2015. And he talks about some nice things like, when they did AlexNet, there was a lot of trial and error. But VGG was a place where they first introduced like a design principle, right? Like say, so for example, here they did trial and error, and let's say all my convolutions are 11 by 11. Here they tried different things and came to 7 by 7. And VGG said, I'm just going to use 3 by 3. So he talks about all of this in these lecture slides, and I thought he did a really good job. And then like after ResNet, like we've been all focused, like the community is focused on making efficient networks. Because okay, how can so with the question, how can we improve accuracy without complexity? So from that question, we have MobileNet, and then some of the things Viru alluded to. We have neural architecture search, which helps to automate some of the architecture design questions. So yeah, this I thought this. So this is lecture 8 for the classification architectures, and then lecture 15 for object detection. Yep. Okay, that's it. Okay, that's all I have for today. Efficient data, I see. Okay, thanks everyone. I think
Thanks.
yeah. Yeah, and if you want to talk about like implementing I've not implemented in Scratch. I've mostly used one of these APIs. So if you have some questions, we can talk about it. Like one of the popular ones now is Mask Rcnn. So if anyone has to use it in their work or just wants to, I'm happy to discuss any questions about that.
So there's a link to this University of Michigan class by
Yeah,
Justin Johnson.
yeah, I'll just share it on. So I took the 2019 because the 2020 lectures are not available on YouTube. Yeah, this one. This is it. And if you just yeah, even there are other things. I really like his teaching style. So there are some things he talks about. Um, Attention. His lecture on attention is really nice. And he talks about some of the things like Joseph, you shared it during the during our CS 224, like the illustrated transformer. And, yeah, I'm finding when I hear the same topic described by different people, it just helps me understand it better. Yeah. Okay.
Yeah, this looks good.
Mhm.
Okay, well, thanks so much. This was a really useful overview of all of progress in object detection and so on. So this is
Yeah.
really good. I know that some of you, Srinivas and Rekil, have done a lot of work in this area too. So
Yeah, it's mhm. Yeah, we use some specific object detectors, but it is if initially I thought I would talk about like a specific object detector, but then you miss all this, like the map and like the key, like the RPNs and all those things, like those concepts extend across these different object detectors. Yeah.
yeah, it's really useful to see it in a historical context.
Mhm.
Okay, well, thanks everyone. This has been great, and I guess we'll see you on Wednesday then. We'll start chapter 15.
Thanks, everybody.
And thanks Viru, and thanks Mehu.